Hello, everyone, and thank you for joining the AstrumDrive podcast. Today, as usual, we are joined by Nelson, and during this session, we're going to review Sprint 9 and what exactly did we do in Sprint 9. So, Nelson, please go ahead and give us some idea about uh, the stories we were able to close.
Hello, everyone. Thank you, Bailo. Let's give a brief summary of what we have done during this sprint. Uh, what we did basically was we worked a lot on the article. We putting together the article, and we worked some new results, very exciting results for the next part of the research, and I will to tell you about that later. But first, let me just summarize very quickly the article, how is this the current article is going, because we start writing, we start putting together the sections, and we find out that we need to give more details about some things, like for instance the how the killing equations tell us about the symmetry we have, and we wanted to be sure that we were having the right symmetries, and we checked that. We found the killing equations. We implemented in Mathematica. It was quite fun to have to do that, and then we figure out to our metric, this spherical symmetric warp drive is it has what we call a timeline killing vector, which is good for the observers we define from the very beginning. And if it has that, if you have this function that defines the bubble independent of time. But we leave this function depending on space, which is the space that it leaves on the hypersurface that defines the space-time. And this is quite nice because this allows you to get more substance in the mathematics, and for instance to allow you to have anisotropies, which is part of the work. Anyway, this is very fine. This is quite nice, and we expect to have this done by this sprint. And I'm really going to enjoy you guys to take a look to this article once it's published. On the other hand, we found so very exciting results, which are related to the fact that we wanted to push in generalizing a bit the metric we already have with the spherical symmetry still, but still, even with the spherical symmetry, we wanted to explore also using, for example, Alcubierre's metric, which is written differently. It's a different metric at the end. It is the Cartesian symmetry. But the point is that the generalization we were proposing is to include a lapse function. This lapse function is a function that comes directly into the construction of the space-time metric in this way. So, and it's usually set to 1, to number 1, just to value 1. We instead of that, we are putting it in a general way. It's time dependent, and it's depending of the coordinates in the radial direction when you talk about spherical symmetry, and in the x, y, and z directions in the Cartesian case. And leaving this open and at this level of generalization, what we found, or we're looking for a way to include more, enrich more the energy momentum tensor. So we check that maybe if we construct the energy momentum tensor based on this metric, we might be able to include, for instance, heat flux, heat dissipation. And we did. That's what we did. And yes, we found that it is quite interesting. It is dependent of this lapse function, the heat flux that you can find if you're constructing correctly the energy momentum tensor. And it's quite perfect, and reduces to the previous cases once you have lapse function equals to 1. So everything works correctly, and it's very exciting to have this because this is a new way of seeing these problems. Now, of course, this means a lot of things from the physical point of view. It's not only that you put the lapse function general, and you have, okay, now we have heat and we have possible dissipations. Well, it has consequences from the point of view of which are the observers that can see these effects. It's not like any observer is the same. So which are the right observers to look at this? And we're forcing all this. And now we have to look into this. We're forcing. Okay, the last function, it means that we don't have any more Eulerian observers. We have different types of observers, and we have to define how these observers are. We have to look into this and set it everything all right so we can see and take this to the final consequences. But this is a great start, and we're very excited about this. We already did it by this to the spherical case, and we work out this Cartesian scenario, which is a lot more complicated. The equations are really messy. Anyway, we're working a lot about this, and basically that's the most exciting news about this spring.
Thank you, Nelson. And do you mind just to go over the stories we were able to close, just to share several words about each one of them?
Sure. I mean, most of the stories are related to the putting together the article, which are, for instance, you can see the stories that is the WDR you see 99, 98, and so on. So in the 99, we just write down, put together what is going on with a section that we want to relate to the anisotropy that is allowed in the system because we live this the spatial dependence in the metric function. We did a bit of work also about what is the local flatness theorem, which is basically a different way of stating the most basic principle in general relativity, which is the equivalence principle. And we took a look at that, and basically this is to check that we are doing the right thing. And it was very good to see that written in that direction. We look an article from this people, Melia, which they did it for the cosmological model, but it applies quite well for our system. There's not much to say about this, because it was more like checking things. We did. Let me put. It's not in the order that is written there, but we wrote down a section putting together all the Einstein's equations with include the cosmological constant, which is part of the work. So we don't have empty space. We at least have cosmological constant, which is something. It's more like to see how the equations behaves. It's not like we are looking for that cosmological constant to be the only source of energy we have. But this is important to make small steps towards understanding the equations. Of course, we wrote down what is it? It's WDR 90 is a motivation, and this motivation is this section is related to why this metric can work. What are the origins of this metric from the point of view of what we think a warp drive is, and how this makes sense as a warp drive metric, and why it is more clear to read, which is a really good advantage comparing with other metrics. Of course, we did field calculations, the field equations. We calculate all of this in the time dependent and then time independent case for instance. And then we generalize this. We generalize using we all did all this together for this article, and we take the next step and put lapse function general, and we did the calculations I already told you, which is quite nice. And basically that's it. That's pretty much what we did in every ticket.
Nelson, I want to talk about a little bit for the dissipation functions and the dissipation equations, which actually are quite big of a deal, because in our warp drive metric right now, we can understand how the warp bubbles are formed and how they're dissipating over time. So it was pretty important advancements. And so I want to discuss a little bit about the next step. So after we're done with the article. So to the best of my understanding, after we're done with the article, we're going to expand on the calculations and we're going to calculate several more special cases, correct?
That's true. I mean, we did have, which is a ticket that I deliberately ignore. It's just we had a ticket that was called special cases. Which what are these special cases? These special cases are once you have the Einstein's equations, you have a system of equations, and in order to solve the system, you need to have a system that is closed in the sense that you I mean, vaguely speaking, in a general way, it's like you have the same number of equations and the same numbers of unknowns. And when you have Einstein's equations, you usually lack of equations. And so you usually the way to solve this is you put by hand, you force one equation, which is the equation of a state. So special cases means that you have a metric which you define from the very beginning, and then you put a new input in the system, which is this equation for state, and each equation for state or is a different case. So you have perfect fluid, you have dust, you have generalizations of perfect fluid, you have perfect fluid with dissipation, with heat flux, you can have an electromagnetic fields, you can have this everything as long as it is consistent with the Einstein's equations you already have. It's not that you put anything you want. You have to be consistent. So this is pretty much the what special cases means. What we figure out in this article, in the current we're writing right now, is that these special cases is a long way of writing and solving equations, and we figure out no, it is better to have solutions, specific solutions. What I mean by specific solutions, so far, what most people do is just show you obtain Einstein's equations because there are some physics. There is some physics that you can take from there because you have a metric and you put the energy momentum tensor. But it's hard to solve the equations. Solve the equations means that you obtain the specific distribution of energy, momentum, mass, and so on, and dissipation, and everything else. So in doing that, it means solving differential equations which are non-linear. So it is hard. So basically, what I'm saying is these special cases that no one now we didn't include in this article. We're going to work on them as a specific work in the future, which means working from the next few sprints on new ways to solve the differential equations. We already have an idea how these differential equations are, and putting special cases, which are very interesting cases because, for instance, you can use polytropic equations of states and have uh, several parameters that you can play with and then obtain different types of distributions. And from these distributions, we start to find out what we need, what we don't need. And if you include dissipation, which is something that I've never seen included in these warp drive scenarios, or heat flux, then we expect to have very interesting results in terms of this. So this is a lot of work that is going to come from the next articles we can have. We think by itself this ticket is it worth just one or even two more articles that we want to work and on the future. So basically, our next step is to work on the calculations, solve the differential equations, and also include the lapse function. This is going to get very messy, but we will figure it out, and we'll see the special cases and start sharing with you guys these nice results.
Thank you very much, Nelson. And also, I want to talk a little bit about our plans for the future, for the next 6 months at least. So when we started working on the Warp Drive project, our vision is to bring it to a lab, to bring the concept to something we can actually test in lab, because we want to make the Warp Drive into reality, something real, something we can use. And in the beginning, it was not very clear to me how we can achieve that, but now I feel that we have a roadmap to that because we spent several months of understanding very well what are the equations describing the warp drives. And now we came with our own metric, we started playing with that. And as a way forward, we see that we want to start using the machine learning and artificial intelligence, also neural networks, possibly to explore and evaluate hundreds of thousands of warp drive metrics and solutions for Einstein equations in order to try to find a metric which is not going to require negative energy and it's going to require like an amount of energy we can actually produce in lab. And this is how we think that we can bring the warp drive up and we can start playing with that and start experimenting. So Nelson, we spoke a little bit about that, but do you mind to comment on this vision for the future and this roadmap?
Oh yes, this is quite exciting in this direction because it's so new from physics and from science. I mean, neural networks and machine learning is a wonderful tool. So the point is like as you already said, we have been working on this for a few months, and we already grasped it a bit. How how is the general behavior of what do you expect from equations and so on. So the point of that is like after solving the equations, we're going to do it during the next few sprints. We will have a very good idea of what is it that you can put or remove from Einstein's equations, from equations of states, and doing that, uh, finding some family of solutions, you can, in principle, make an extrapolation and see which are, if I change this or that, which is the metric that can give me this type of solutions. And of course, this is something preliminary, and this is a very good idea. But the point is like it's going to help us because see, we can find some parametric form of finding metrics solutions. It means that you can explore a lot of all the principles. I mean, basically, what you said to the system is like, okay, please learn how to solve this and give me some solutions. And that's one thing. Another thing that I'm really excited to explore is like, what is it about the symmetries? Because it's not the same. It's completely different when you have different metrics with different symmetries. So one thing that I'm quite interested is in if can I give some input and the system can give me the specific symmetry I want, and this is quite exciting to see how much we can generalize this and all these inputs that we can find. And this is going to work not just for these warp drive problems. I think I'm going to open a possibility of solving problems in many fields, not only in general relativity, of course in warp drives, but in many problems in other fields of physics. So we are opening a big door here, I believe.
I agree, Nelson. I cannot agree more. And I want to comment this door a little bit more. So as we know, the whole thing about the warp drive started in the beginning of the 90s when Alcubierre was able to construct a metric, which is a valid metric from a physical standpoint because it is solving the Einstein equation. So we know that mathematically it is all right. But the problem with the Alcubierre metric is that it's not practical. We cannot really build something based on this metric because it requires huge amounts of negative energy. So what we're trying to achieve right now is to build an AI system which is going to evaluate hundreds of thousands and potentially millions of warp drive metrics in order to try to find one which doesn't require negative energy, which doesn't require big amounts of energy, something we can start playing with in lab. And this is the general direction in which we're going to go. So it's really exciting, actually, understanding how the equation works, how we can solve them, how to build a neural network which is solving this equation. So it's super exciting for us. And of course, we're going to keep you guys posted about our progress and our research. And having said that, Nelson, do you have anything else you want to add to the session today? Anything?
No, I think we basically touch all the more important points. And I just want to say maybe that please, guys, interact with us. Tell us what you think. Tell us what is in your mind. And if you feel like you can collaborate or you have any idea, just don't hesitate and leave us the comment there right down. And if you can support us, of course, it will be really amazing. Thank you.
Thank you very much, Nelson. Thanks to everyone who is listening to this podcast. If you feel like supporting us, you can do this on Patreon. Otherwise, please share and like the video. And with that, thank you for listening, and I wish to all of you to have a very nice and successful week.